if you have a signal like ft, then this could be any signal, okay? Then you put to the system. We call it a system, like a filter or whatever, or that I call it HT. Then you get another signal which is GT. Do you know the relation between these three? The convolution. Have you heard about convolution? No, convolution. Yes. Because HT, what is HT? I didn't tell you. This is impulse response. So each system, if system especially is linear, you know it's very difficult to talk about nonlinear signal or nonlinear system. But usually our real system or the behavior is nonlinear. But we can how to say, we can divide for small portion of time. In that small portion of time, the system becomes linear. Then you are processing in that. For instance, the vocal cavity of what I'm talking to you, there is a system from my lung comes the pressure of the lung, then vibration of the cord, then the glue of the mouth and also the nose. Then the output after this, the filter is the inside the vibration of my tongue, cord, everything. That there is a system. So this system is changing, the parameter is changing always. So it is not very linear, it's very nonlinear. But for instance, in 10 milliseconds, people they say, in 10 milliseconds you can assume that this is linear system, for instance. So, how to retract or I don't know if this is okay, or obtain the HT. How to obtain HT? If you put a delta function here, do you know delta? Delta function is like this. Just at zero, there is infinite with energy of 1. So an impulse, that is impulse. So you are, for instance, you are making 1, then there is vibration of this table. You put 1, then vibration. So you can do it for everything. This after putting to this system, this is only this. Well, in digital image, digital signal, instead of this we just put, because it's discrete, at 0 you put only 1. Very, just simple, 0, 1 at time 0. Then at time 1 or 2, this is sampling, for instance, you don't have anything. But what is GT then? GT, the output becomes like this. For instance, like this, then something like that. The response of this after putting delta to HT, then become GT. For instance, this is GT. But after putting, so what is this? It means that actually this GT is HT. because we'll be saying, I put it like a box here, better not to write box here, just say. So this G, when delta put to the HD, then this become equal to HD. So then you are finding the impulse response of the system. Why? That's the what we call it, impulse response. The response to an impulse. This obtained from general. For instance, how define this is definition of the delta. At 0, here is a little bit incorrect. Delta t is infinite at 0 times 0. Then otherwise, others is 0. So, but the integral, the energy of this from minus epsilon, very small portion to plus very small portion. It's like this, that you have a pulse, then narrow the pulse to very infinitesimal, very small. Then, because the energy is 1, this becomes 1. Because the amplitude becomes infinite, but infinite multiplied by 0 is 1, for instance, in this case. The energy is 1. This is definition of delta. This is actually a little bit wrong, it's round here, but actually it should be delta, and this is infinite. This is in analog. The same is in digital, that as I told you, just put 0, 1. Then how to define mathematically? Mathematically is this formula. H tau, ft minus tau, d tau from minus infinity. So for when you find the ht for any signal like ft, you can find gt by convolutional. This is convolutional integral. This is very general formula that I hope you remember this. The convolution integral is the relation between, well, in general, when you put ft here, signal ft, then gt is integral minus infinity plus infinity, h tau is different variable multiplied by ft minus tau d tau. This is convolution, integral convolution. You can also say in other form, like we see some form is more, especially in digital signal processing, this form is much convenient. This is same, f tau ht minus tau. But this is an integral over tau. The function is the function that came out is a variable of t. Tau is eliminated here. So you can write like this one. This is important for a linear system. If you have the impulse response and the input, then you can calculate the output. So another form that we are writing Ft is Ft star with model or just a star or other side you can write Ht, asteristic Ft. This doesn't mean normal multiplication. This is complicated convolution integral. So we show by asteristic here. This is just multiplication, but you are integrating, and then this is convolution. You are not tired? You are not tired? You can refresh. And there are some properties. Let's go faster. Frequency domain. Well, if you want to go to frequency domain, the time domain, go to frequency. You know about Fourier Transform? This is Fourier Transform. When you have a time domain signal or system, then when you see the frequency domain, omega is 2 pi f, which is the frequency. Usually, this is lowercase, this is upper, we write it uppercase. So in frequency domain, you can write g omega is integral. This is very mathematical, I mean, general case. But in digital signal processing, we can just don't use the minus infinity to plus infinity. Rather, we have different filters like FIR or IIR. So it is very simple. E minus j omega t dt. The integral here is over time. What is omega here is the variable of frequency. So the result is variable of frequency. The time function becomes frequency function. This is frequency domain or Fourier Transform. Fourier Transform is this. This is general definition, which omega is 2 pi f. Like you have a set there, and this is 2 pi here, and then you are rounding it, and then omega is something like this, that it is velocity, angular velocity. Very good thing here, especially in our, when we are computing, because signal processing, when it is easy to use, is that you should be you should implement the system, not the theory. Just theory cannot be implemented. So you have to reduce the size of the computation, because even the very big high performance computer or chip cannot perform a lot of computation in one portion, very small portion of time. For instance, your sampling frequency is megahertz or gigahertz down. It's very complicated. So how you make this computation small? Because this kind of computation is very complicated. Later I will tell you, this is power of 2 of number of this. For instance, sample is n to power 2. Computation you need, especially in fixed point processor, you need more the multiplication is more difficult calculation. But if you go to frequency domain, then you can simply write G omega is equal F omega multiplied by H omega. This is just normal multiplication. So each beam, I call it beam of frequency, but is obtained from that beam multiplied by the same. If I should draw here, for instance, if you have a ft here, then you have f omega here in parallel. So this is Fourier transform. This is Fourier frequency transform. Then f omega is here. For instance, omega 0, omega, well, it is multiplication of omega. For instance, 1 omega, and then 2 omega 0, then to f n omega 0, for instance. Then if you have h here, ht here, and frequency transform, make it transform, then h is here. The same beam, this is beam. This beam multiplied by this multiplied by this is the G omega 0. And again the same. This one by this one, G omega, for instance, 1 omega is 1 omega, 0 omega, 2 omega, for instance, or so on. So each one, just multiplying n times, we can obtain the Fourier transform. Then this Fourier transform can be inverse Fourier transform, and then you get GT. It's very simple implementation of the convolution in the frequency domain. I will show you how you are reducing when you are making bulk data of window. For instance, you have 8,000 more, 8 kilo or more data in 1 second, processing the speech or other. So this is very good, just for implementation is very important. Well, again, I came back to unity pulse response. This is what I told you. But in digital, just simple equation is for digital is this. Delta n is 1 for n 0, not is 0 for not n equal. For instance, in discrete, this was in honor. Okay. So when you go to discrete, things is different. If you go to discrete, then you define delta n. Delta n is simple, just 1 for n equals 0, and for n equal not 0 is 0. So it's like simple, like I told you. This is delta n. Again, another important function in DSP I define here. Unit step function. This is Dirac-Delta function, and this is this, and unit step function. Unit step function is like this, but you have a step like this. 0, 1, 2, 3. I don't write the sequence of, for instance, this is nt. The period is t. So here is 1, here is 1, 1, 1, 1, all 1. So it's like a step. So how you can say you call it the step function, which is 1 for n more than or equal 0 and 0 for n negative. Here is 0. So it is go to infinite. There are very interesting mathematical relation between these two. N is integer, of course. So soon I will finish. For instance, you can calculate this kind of thing. Can you calculate? For instance, un is from this is the delta k for k minus infinity to n is un. Or you can say that the same from 0 to infinity is n. This is very important. For instance, the relation between delta function, the step function, that then here I'm trying to define for you the delay. What is the delay in a signal? Because you are putting a signal, a step function. This is from 0 to or 1. This is un. If you want to make a un minus 1, what you say? So argument 0 is 1. Where this argument is 0, when n is, if you want to make a un minus 1, means you are shifting to the right. You shift the data to the right. So at 0, well, this is n, of course. So n is 0 is minus 1, so no meaning. But at 1, argument is 0. So it means that this came here, shifted to right. Shifted to right, and so on. So this and this is one signal. This is only for one simple example, the step function. When you are shifting to the right, you cannot shift to left because it's causal system. Causal system is physically possible. You can always delay. You cannot advance in time. You can predict the future, but I mean not predict the future, but the past is possible to determine, but the future we don't know. So always it's n plus 1, we don't know. N plus 1 is here. We don't know. In time negative, we don't know. So these two, if you make a subtraction of this, what obtain? Subtraction. Sample by sample. At 0, you have un minus 1. Because 1 minus 0 is 0, so this is 1. How about 2? This is 0, this is 1. At sample 1, this sample minus this sample becomes 0, and so on. This is same as this. This is 0. So then this is delta. So this relation is easily, proved. The other two relations also very easily solved. mathematical relation between simple discrete function. This is one example. So, you know what is the shift to right, you know the delay by one sample. We have time 2:20. We should finish, but we are tired. Actually, I want to, for instance, time invariant system. But we have several things here for time invariant system that this is output. This is the convolution for, you can see by yourself. This is convolution and page number 9. Instead of integration, we write summation. Hi is integer, hn minus 1. So this is general. This is output of yn related to xn and impulse response of, what's this? Impulse response of hn. So this is convolution in discrete. Discrete convolution, instead of integral, you use summation. You can write in this form. And then you put delta in here, as I told you, you find hn. So this is time invariant still. So then we define for you a finite impulse response and infinite impulse response. You can see finite impulse response system is the system that has finite. The h is finite. Infinite impulse response is just to infinite has response. It doesn't, maybe converge to 0, but still there is. This you can study, doesn't matter. Then causal system. Causal system is if n is 0 for, like this system. For n negative, this is causal, this physical system. So I go faster. And then go to FIR. What I wanted to tell you this time was then property of the, when there is some filter here. Linear shift invariant. For instance, let's go here. Number 15. If the system is linear, page number 15. If system is linear, then you have two input, x1 and x2, multiplied by two constant, a1 and a2, and then add together at the input side. So a linear, this is linear combination. I don't write here because maybe you don't have time. And then this t is a mapping, like a function. This is a system, t map this input to output. So we call it y dash. On the other side, on the other hand, if you do this, we have the same map or function. x1 map to y1, x2 map to y2. So at the output you make the same linear combination, means that multiply by a1, multiply by a2. So this y1 multiplied by a1, a2 multiplied. So then add together. This is y double dash, okay? If these two are equal, then the system is linear. Simple. So if I give you an example, for instance, simply because that book is too complicated to meet, for instance, if I give you one example here. write this for this function. Y t is, well, let's say yn, discrete, yn. T is equal, for instance, something is 1, so assume it's 1. So t is 3xn. This is output is in minus 4x n minus 3. Minus 3 is 3 something shifted to the right. So it's such a signal, can you prove it?